Okay, a few minutes late, technical troubles, but anyway, we are going to start. Good. So today's lecture is basically on acids, bases, and everything that can be connected to that acids and bases. I suppose we'll be able to check a few problems. How do we solve them? How do we calculate some interesting parameters? And at the end of the lecture, I will give you some sort of overview where you can see pH acting in biology, in chemistry, and so on. So first, what I want to start with is basically the question about solvation. The thing is that the processes are pretty different whether we are performing them in some sort of solution. For us, of course, the most interesting solvent is water, so we will be basically speaking about solutions in water. And maybe these numbers don't tell you much at this point. We'll get to that in the next lectures. But what is this everything telling to us? That if we have hydrochloric acid in the solution, so in water, it certainly dissociates and transforms into two ions, H plus and chlorine minus. That's a spontaneous process and pretty rapid process. If you try to perform the same thing in a gaseous phase, you'll not be able to do that. You need to invest a large amount of energy to transform this molecule into two ions of H plus and chlorine minus. So it's no dissociation at all. It's probably one molecule in 10 to 240 molecules will dissociate at will. So there is something pretty different going on in the solution, and we should keep in mind that ions are no longer isolated, but they are solvated. Here's an example of a solvation. So by the IUPAC definition, solvation is an interaction of a solid with a solvent which leads to stabilization of the solid species in the solution. So we know that water has polar molecules. We have considered different kinds of molecules, and you probably have seen that it has some dipole moment, and thus if you have something that has charge in water, it will try to reorient somehow and screen this charge from the environment. That basically stabilizes the charge. In case of water, we can call solvation, we can call hydration. So what else? If we have a proton in the water, it is solvated as well as anything else that has charge, and it basically transforms in something that we call a hydronium ion, and we write that as H3O plus. So here is an example. We have a proton, and it is solvated, and we consider that as some form of interaction between a proton and a molecule of water. So at the point, nothing really special. Here are a few more structures for solvated hydronium ions and different dashed dashes. They represent hydrogen bonds. So these are just a few examples. What else? Interesting thing is hopping of protons in water. So here is an example of so-called Grotthus mechanism. Sounds like something from Harry Potter, I guess. You see when one proton is basically connected to one water molecule, but it can be transferred to another water molecule, which transfers its proton to another water molecule, so on and so forth. So if you consider the electrical mobility of different cations, you can see that hydrogen ions or just protons, they are incredibly mobile. So that's basically due to this mechanism. This mechanism may resemble you something that you saw previously if you thought about, I don't know, electricity. So if you have a wire, the electrons that you put on one end of the wire are definitely not the same electrons that you will get from the other end of the wire. But basically we know that electricity travels through wire quite quickly. And it's not because electrons are traveling so quickly. No, they are not at all. But we are putting some electron on one side and we are taking some pretty different electron from another side. So here is very similar case. And here is one example from the biology. If you can see this small picture, that's an aquaporine water channel. How do you think, just by its name, so what is it for, this aquaporine channel?
Pumping water into the cell.
Well, not pumping, just letting it go through the cell wall. So it allows water molecules to pass through. Because you know that this lipid bilayer, it will not allow water to go in or out, and if for some reason we need to do that, here is a special protein. What's interesting in this protein, you see these small plus charges in here. Basically, since water molecules are polar, so they have some dipole moment, when moving through this channel, water molecule will most likely try to look with the oxygen in the direction of this positive charge. That's because we have some partial minus charge on the oxygen, so I hope that you remember all that. So here we have some sort of dipole moment, so some partial plus charge on the hydrogens and minus charge on the oxygen, because it is more electronegative. And what it leads to, that's basically, this is the mechanism to break this chains, and not allow protons to go from the outside of the cell or from the inside to the outside. So we want to transfer water, but we don't want to transfer protons. And you might guess that cells are trying to keep a certain balance of different anions, cations on the outside, on the inside, so they will not really like if protons will just go around as they wish. Okay. What else? So what do we know? So protons are highly reactive. So in fact, an isolated proton is so reactive that it will even add to a molecule of a methane. And you can pretty see that during the mass spectroscopy. So if you return to the lecture number 2 and consider in more details mass spectroscopy, you can probably find something like that. Protons solvate, we saw that, they rapidly move in water, and since protons are so interesting to us, we will probably want somehow to characterize solutions with the concentration of protons that we have, because we are concerned with their fate, and we know that they can significantly influence the chemistry of different processes that we perform in the solution. Sorry. Just a few notes. Different books, they use interchangeably concentration of H plus and H3O plus. Well, that's basically because we cannot consider an isolated proton as existing. It is always solvated, so you can consider that as a part of some water molecules or connected to that. So these two things are interchangeable, and I will write in some places H plus, somewhere H3O plus. Just never mind that and consider it's pretty the same thing. So okay. Since we are concerned about the concentration of the protons, we should measure that. But it turns out that this concentration, it may change wildly. So there's really large variance of what we can have. So we skip to the so-called logarithmic scale. So this is probably one of the formulas that we will use at most. The definition of the pH. So pH is minus logarithm of the concentration of protons. Well, the same thing would be if I write here just H plus. So doesn't really matter. Absolutely the same. Please note that this is logarithm base 10. So I can write that as I don't know, as log base 10. So it's not natural logarithm that you may be more familiar with, but nothing really special. And here are some substances that we have, some dairy products, some household chemicals, and their pHs. So here is the neutral pH of 7. We'll talk in a moment why it's 7. And here are different chemicals. Okay. And this is the slide I probably want you to consider more accurately. This is the autoprotolysis of water. Here you see a reaction when two water molecules are reacting and creating basically H3O, so hydronium ion, and OH minus. Here is this reaction depicted in form of some sort of 3D spheres, so you see how that happens. And now we are concerned with the notion of dynamic equilibrium. So a dynamic equilibrium means that some processes are going on in the solution or whatever we are considering, but the overall result of these processes is that they compensate each other. So all the time some water molecules are transformed into these two ions, H3O plus and OH minus. It's always happened. And all the time these sort of ions are combining back to give you water. When the dynamic equilibrium is achieved, so we gave some time for the solution for all these things to settle, we know that how much of these ions are created, the same amount is transformed back into water. So always something is happening, but if we calculate the overall number of the ions, of the water molecules and so on, these overall numbers will not change. And here is this idea expressed more mathematically. So this is all going on in the bottle of water. So if we look at some reactions, so at two molecules that are interacting, it may be two water molecules. So what is the probability that these two interacting molecules are water molecules? That's basically concentration of water times concentration of water. So this part. So this is the probability that two water molecules hit each other. With certain probability, reaction may go forward. So if it was some sort of productive interaction, and we will get this sort of ions. We designate that as some sort of constant, so it's just an approximation, but it's pretty good working, so we'll go with that. On the other hand, if the reaction is between H3O and OH minus, so what is the probability that if I look at two molecules that are hitting each other, these are H3O plus and OH minus, that the concentration of H3O plus, because the concentration is basically let's say proportional to the probability that randomly chosen molecule is exactly of that kind, times the concentration of OH minus, and well, if all the rest thing we compress into one constant, we will get this expression, the probability of transforming back. If this is dynamic equilibrium, they should be equal. So how much transform one way, the same number transforms another way. So we set the sign equals here. And that's what we need. After we roll the thing, we can rearrange that a little bit and we get something like this. I'm so insisting on this formula because we will see pretty similar formulae in the later lectures. Especially, I guess, lecture number 5, I'm planning to tell you something about all these things. So we will see pretty similar formulae. So if you understand that now, you'll have no troubles there. So that's why. So okay, what else? We know that there is a lot of water in this solution. So basically, this may be just water itself. So we may suppose that the concentration of water does not change significantly. So it's pretty constant. So this part is some number not quite interesting. So we multiply by that, and I'm not sure why it's not showing to us the lower part of the slide. Maybe I'll make it smaller and return to the previous slide. We can define the constant of Kw, that is basically result of the multiplication of H3 concentrations of the H3O plus and OH minus, and the measurements of this parameter. So this is an experimentally measured thing at room temperature 25 degrees C, gives you 10 to the minus 14 moles squared per decimeter minus 6. So that's what we have. So this is a measurable parameter. We can measure that. We can have it. Good. What else? I told you that I will say Y7 is basically the neutral pH. So we consider as neutral just regular water. So we have water, we consider that is neutral. Okay, we know that in water, Kw is equal to this result of this multiplication, and it is 10 to the minus 14. But if that is a clear water, where do we get all these ions? They can come just from the water. And this process basically creates you the equal number of the plus ions, so H3O plus and OH minus, so their concentrations should be equal. Thus, if we have measured the thing and we know it's 10 to the minus 14 and we know that these two things are equal, we can calculate them as 10 to the minus 7. If we now calculate pH, that is minus logarithm base 10 from this value, so logarithm base 10 gives you minus 7, and minus of the minus 7 will give you 7. That's what we have. One small note, if we calculate pKw, you see this notion of p's. It's quite interesting. Whenever you see in chemistry this p, it means that you are taking logarithm base 10 from minus logarithm base 10 from whatever is after this p. So p of Kw is by definition minus logarithm base 10 from Kw. So Kw was 10 to the minus 14. You calculate that, you get some number. But the interesting thing is that if you use this part, if you use the definition of the Kw, you can find out that it is equal to the pH plus pOH. So pH plus pOH is always equal to 14. That's what we have, and we will probably use that. Just a small reminder that pKw is a result of the measurement, and it may depend on some different parameters. For example, water dissociation occurs endothermically due to electric field fluctuation and so on. So increase in temperature shifts the equilibrium to the right. So thus increasing the temperature, you see that pKw gets smaller and smaller. We will not use this much, but just for you to notice that it may depend on the temperature. So if that happens, that you calculate something for different temperatures and so on, maybe it may play some role. Once again, some just small scale of different dairy products and common chemicals that you may encounter, and their pHs and pOHs. Since now we know how pKw and all the things are connected, I guess once again I should go to smaller size. Oh great, it fixed itself. I don't know how. You may use this sort of equation and you might see that pOH times concentration of OHs and H pluses, if you multiply them, you should always get this sort of constant. So if you know one of them, you can calculate the other. That's really easy. And the sum of pH and pOH is always 14, so you can check that as well. Once again, I remind you that whenever you see in chemistry some sort of p in here, that means minus logarithm base 10 of whatever is after. So OH minus, we can measure the concentration of OH minus, we have that. We take logarithm base 10, we do minus, and we get pOH. Pretty simple, I guess. Okay, but protons, they come not just from the water, but there may be some different sources of protons in our solution. And here is, and where do they come from? They come from acids. Regarding acids, there are basically a few different definitions of acids and bases. At school, you probably studied the definitions of Arrhenius, I guess. So by Arrhenius, acid is something that can donate a proton. So if a chemical can donate a proton, by Arrhenius, that's an acid. If it was able to donate something like OH minus, by Arrhenius, that was considered as base. In this lecture, we will use the definition of Brønsted-Lowry. So Brønsted-Lowry acid, basically the same, a substance that can donate a proton, and Brønsted-Lowry base is a substance that can accept a proton. Here's a little bit, this part is a little bit different. So if by Arrhenius you considered sodium OH as a base, by Brønsted-Lowry that will not be a base. But OH minus by Brønsted-Lowry will be a base, while sodium plus is just some sort of spectator ion, so it's not really capable of doing something interesting. Okay. And this, there is third definition, so-called Lewis acids. It is a little bit broader than Brønsted-Lowry. It involves an acid. It's not just a substance that donates proton, but it also substances that can accept electrons will be called Lewis acids as well. But there is, let's say, such a difference that for these acids, for Brønsted-Lowry acids, we have a good measurement of how strong is the acid. For Lewis acids, at least I don't know such sort of measurement, so how to measure that, so how to quantify that in some sort of numerical way. But for Brønsted-Lowry, that's pretty okay, and we will get to that just in a couple of slides. So here is an example. Here is the hydrochloric acid, and here is the water acting as a base in this case, and hydrogen from the hydrochloric acid is basically transferred to the water, creating the hydronium ion and a chlorine chlorine anion. Okay. This definition is valid not only in liquid phase, but which is actually the most interesting for us, but in other phases as well. So here is a gaseous phase. You see two bottles here. So one contains hydrochloric acid, the other one contains NH3, and you see the reaction when proton is transferred to NH3 and two ions are created, and you can see that as some sort of white smoke. So if you work in chemical labs, so please never keep these, always keep these chemicals apart and well closed. Otherwise, you get a lot of white smoke everywhere in in wherever you keep them, and I don't think it's it's worth time spending it to scrape off all that white powder. So yes, keep them away from each other. What else? Any acid and any base, you can write this sort of reaction. So here is an acid. We specifically draw some sort of hydrogen that will be transferred to somewhere. Well, to look better, let's say. And here is a base. They undergo some sort of reaction. With these arrows, you see that this reaction is probably in some sort of equilibrium, and you see that the proton is transferred to the base, so we get BH plus, and here is some sort of anion from the acid. So this anion is called conjugate base. So conjugate base of the acid AH is A minus. B is the base, while BH plus is its conjugate acid. So every acid has a conjugate base that is associated with it, and every base has a conjugate acid associated with it. So it's always the case. So acid is dropping a proton and you get the conjugate base. Base is accepting a proton and you get conjugate acid. I guess we'll use that a bit later. Now here is an example of water acting both as acid and as a base. It can do the both, it's pretty okay. So here we have acid HNO2. It transfers its proton to water and we get hydronium ion H3O plus and it is transformed into conjugate base NO minus NO2 minus. Here water worked as a base. Why? Because it has accepted one proton. Here is another case. We have a base and we have water acting as an acid. So what does the base? By the Brønsted-Lowry.
It receives a proton?
Yes, it should accept one proton. So in this case, NH3 accepts proton and becomes NH4 plus, and this is a conjugate acid to the base NH3. Water worked in this case as an acid. It dropped one proton and transformed into conjugate base OH minus. Okay, for the future we will always suppose water as solvent, so it's probably will be always available, and we will suppose that it has some pretty high concentration. H3O plus and... Oh, I see a question. Yes, please.
Yes, so in which case water will receive a proton and in which case it will like share a proton? What it depends on?
If you are adding an acid to water, and if this acid is strong enough, We will get in a moment to the notion of pKa's. So if its pKa is low enough, because the acidic side is low pKa's, it will be able to transfer its proton to water. So it will take its proton and give it to water, creating basically this thing. If we have a base in water, and this is pretty strong base, it can remove proton from water. So once again, we shall look at so-called pKa's and what they do. If pKa is somewhere near neutral value, something like that, there will be probably some dynamic equilibrium with some non-dissociated acid, and some part will be dissociated. So I guess we'll get to that just in a couple of slides, and I will show you that parameters. Okay, so pH meter measures concentration of H+. That's, we are taking a note, so we can measure that. And once again, I'm reminding you about the equation that H+ times OH- should give you this value. Okay. Here is just some sort of example. Here is an acidic solution, so it's hydrochloric acid. This is a strong acid, it fully dissociates. So basically all its hydrogens will be attached to waters. You remember that H+ and H3O+ are interchangeable. And here you see in acidic solution you have much more H+ than OH-, but there, if you multiply the concentrations, they still give you the same number. Why? Because this is just a dynamic equilibrium for the reaction of H+ OH- combined into water. If you add more H+, they will, let's say you just started adding H+, they will start finding OH- and transform them into water. So the concentration of OH- will drop down, while this H+ went up because you added them. But the overall equilibrium will be reached when the product of these concentrations is equal to this number. So please keep that in mind. In neutral solution, we talked about that, just plain water, and we have the equal amount of H+ and OH-, and this product, of course, is 10 to -14. Basic solution, you added something, let's say sodium hydroxide, that is given off OH-, you have much more OH-, but this sort of product will still give you 10 to the -14. Okay. What else? Yes, we are getting to that part. So acids may not fully dissociate. So depending on the dissociation level of the acid, we can call that strong, weak, or negligible. So it's like not considered as an acid. Strong acids, they fully dissociate. So how much you add that, it will just transform into ions, and all the protons it had will be transferred to water. So strong acids are fully transferring their protons to water. This is basically the reaction, and we need somehow to quantify this reaction. So the strength of the acid is quantified on the basis where is the equilibrium of this reaction. If it is shifted to the right, this is a strong acid, so it transfers protons to water. If it is shifted more to the left, it is weak acid. It has no such ability to transfer all protons to the water, and it transfers just some of them. Once again, you see this equation. It's pretty similar to the equation I have shown you already, yes? So here is concentration of H3O times concentration of A-. So here they are. Multiplying these concentrations basically tells us the probability of these two molecules hitting each other. And here we have on the left side the concentration of the acid, AH, here it is, and water, here it is. Once again, if we suppose that the concentration of water is not significantly changing during the course of the reaction, we just multiply by that and get a new coefficient called Ka. Here's a fun fact for you. How do you think, what is the concentration of water in water? Is that some sort of reasonable number or whatever?
In distilled water, 100%.
You may think of that like 100%, but we are but you see what's the point? We are measuring concentrations in moles per liter. So that's basically why this question is a bit tricky. So these brackets means concentration, but this is concentration measured in moles per liter. Zero? No, it's not zero. That would be a bit strange. That's some sort of reasonable number. So you can calculate, if you have a liter of water, it weighs 1 kilogram. You know that 1 mole of water weighs 18 grams. So you can calculate the number of moles of water in 1 liter. And that will be basically the concentration in moles per liter. If you do the math, you should get something like this: 55.56 mole, where decimeter cubed, it's 1 liter actually. So concentration of water in water is something like 55, 56, so something like that. Why? Because we measure in moles per liter. So please be attentive. When we have all these sort of formulae and you will need to calculate something for the homework, please remember all concentrations in moles per liter. And you have probably seen some, I don't know, some flasks with something like this, 1 and big M, which means 1 molar solution. This M means moles per liter. So 1 M is basically solution that contains something, I don't know, hydrochloric acid, for example, in the concentration 1 mole per liter. Yeah, so please keep that in mind. So don't use some sort of percents or something like that. In chemistry, we do moles per liter. Good. Now, pKa. Once again, if I write p, that's negative logarithm base 10 from something, in this case, Ka. Because of the minus sign in this definition, the lower pKa, the larger the equilibrium constant Ka, and hence the stronger the acid. So if you see pKa that is low, I don't know, 1 for example, that's a really strong acid. If it is something near 7, it's not an acid. So the pKa of the acid is the pH where it is exactly half dissociated. So half of the molecules of the acid transform into ionic form when pH is equal to pKa. If pHs at pHs that are above the pKa, the acid exists more as in the dissociated form. If they are lower, it tends to exist in the non-dissociated form. Okay, tricky question for you. I hope we will have some time for that. why pKa is pH when acid is half dissociated? Can you guess from these two formulae? That's basically all you need. Well, and definition of pH, but okay. Yes, because A minus is equal to AH, well, in concentration, because half of them is dissociated. So you remember we calculate molar concentration, so half of moles have dissociated, they are equal. So you can basically divide through, because they are equal, we remove them. So Ka in this case is equal to H3O plus. And if I take minus logarithm, that's basically taking minus logarithm of H3O plus concentration, that is pH by definition. Okay. Some more things about solutions, dilutions, and so on. Once again, an example. So we have reaction, an acid reacting with water, and we get H3O plus and A minus. For weak acids, we can write, let's say, few formulae. So acids that are not fully dissociated or are weakly dissociating. So here is an equation for Ka. I guess it would be better if I wrote this is concentration initial, so before anything has happened. So I just added, and the acid had no time to dissociate, and this is just our HA in the solution. So I can write Ka by definition as it is, but this equation tells us that we are creating A3O plus and A minus in equal amount. We disregard the auto-ionization of water. So despite the acid is weak, it still creates much more hydronium ions than water itself. We'll see that in problems. And that's why these two are equal, and let's say they are equal to some x, while this one down is basically the initial value that we have minus the part that has dissociated, minus x. If this x is small compared to the initial concentration, that is pretty reasonable for weak acids, we can write down equation for this x and find that it is equal square root of Ka times concentration of H HA initial. It's really good because we know the initial concentration, and you can calculate how many H plus ions will be created, what will be their concentration, in case if the acid has parameter Ka. These all are measurable parameters, so you can just grab a table that contains all these Kas, pKas, and so on, and just look up in the table for your acid of interest. Same thing can be written for bases, but here we use not Ka but Kb because it's K for base. Okay, so one more example. So here we have strong acid and weak acid, just to look on that. So if we have a strong acid, it fully dissociates, and you see that we have just anions, so A minus, and hydronium ions created with the reaction with water. If we have weak acid, there will be some sort of equilibrium, so you see different arrows here. So this arrow shows that reaction goes almost to completion, so you don't expect anything any leftovers, while here will be some sort of dynamic equilibrium, and you will find in the solution not only A minus and H3O plus, but undissociated acid HA as shown in here. So so all these species can be found there, and you can calculate their concentrations. Okay. So once again, strong acid completely transfers its protons to water, leaving essentially no undissociated molecules in the solution. Weak acid only partially dissociates in aqueous solution and therefore exists in the solution as a mixture of undissociated acid and its conjugate base. If a substance has negligible acidity, it contains hydrogen but does not demonstrate any acidic behavior. What else? If the acid is strong, it is conjugated with the negligible base. So strong acid means that the conjugated base is almost, you cannot consider that as a base, actually. It doesn't do anything. If your acid is weak, the conjugated base will be weak. If this is a substance with negligible acidity, you will get a strong conjugate base. That's okay. So here we have some sort of scale that tells us that the strongest base in the aqueous solution is always OH minus, and the strongest acid is always H3O plus. The reason for that is that if you add stronger acid, it just transfers its protons to water and gives you H3O plus by protonation. If you add some stronger base than OH minus, it will just deprotonate the water, take its protons and create you a lot of OH minuses. So that's the best you can get in water. In different solutions you can get something different, so that's pretty possible. Okay, and here is some sort of scale, once again reminding you that pH 7 is neutral, and here we have reaction pH for the reaction H3O and to H2O, and here reaction H2O to OH minus. So if you see some substances with pKa's lower than minus 1.74 or higher than 1574, they will fully dissociate, and basically you can consider them as something really strong. Okay, here is some sort of scale of strong acids, weak acids, and some things with negligible acidity. So here you can see how do they look like if we sort them with respect to their pKa's. We will get, I guess there should be some table with pKa's, but let's look at this one. So here you have H3O. That's the strongest acid you can have in water. So whatever is stronger, it fully dissociates, so it just transforms, let's say H-chlor transforms into chlorine minus and H plus, and so on. You have weak acids, they have pKa somewhere here in between that values I showed you, and they partially dissociate. And here are some things that are not considered as acids completely. Similar scale for bases, it just goes the other way around. So strong bases are down here, they are pretty willing to accept a proton. Weak bases are in between, and negligible bases are somewhere there, they do not want to accept any protons. Great. Now we have our first problem to consider. And I guess it's really good because you will have something similar to do at home. Let me just check where we are in the presentation so I can adjust time accordingly. Okay. I think we can consider a few problems and then make a break, if you will, if you wish. So yes, let's let's first consider a few problems because you will have to do something quite similar at home. Here is an example of a strong acid. So what means the acid is strong? It fully dissociates. So there is a complete ionization of the acid. So here is HNO3 and it dissociates. It gives you NO3 minus and H3O plus. Good. This is a monoprotic acid, so it has just one hydrogen it can give off. So this means that for every mole of this acid, we will get 1 mole of H3O plus, because it fully dissociates. So how much you have added, the same much H pluses you get. And of course you will have the same amount of conjugated base. For diprotic acid, situation may be a bit more complicated, but I will not consider that. So let's consider we have 0.2 molar solution of the HNO3 plus. I can neglect the auto-ionization of water. Why? Because if this fully dissociates, I have the concentration of 0.2 moles per liter of H pluses that come from the HNO3. If you remember, for water there's much less. So the H pluses that come from water, they have something like 10 to the minus 7 moles per liter. So that's negligible. I can forget about it. But if the concentration of acid will be something like 10 to the minus 6th of mole per liter or less, that would be preferable to consider water auto-ionization as well, but here we can drop that. Okay, so 0.2. Now, what is the pH? Since we dropped the auto-ionization of water, basically all H pluses are coming from the acid, and acid fully dissociates. So this means that the concentration of H plus in the solution will be 0.2 moles per liter. I can plug this number in. So here the equation, so definition of the pH. I plug it in and I get the result. Okay, so does everyone understand what happened? Okay, so no questions.
Where did excuse me, I have a question.
Yes,
Where
please.
did 0.7 come from? Because shouldn't it like minus log 10 of 0.2 be like minus 2 or something?
Please remember, so if you are taking logarithm, you can get negative values. So logarithm base 10 of 10 will give you 1 because it's 10 to the base 1. Now logarithm base 10 of 1 is equal to what? So what's the number? What should be the power of 10 so I can get 1? Oh,
0?
Yes, it's 0. Absolutely correct. It should be 0, so logarithm of 1 is equal to 0. And if I take logarithm of something smaller than 1, I will get negative values. If I take logarithm of 0.1, this is basically 10 to the minus 1. So when taking logarithm of a number that is smaller than 1, I get a negative value because it's smaller than 1. I need to put 10 to some power that is less than 0 to get this number. And this minus is then compensated with this minus that comes from the definition of the pH. So that's why we get a positive number at the end of the day.
Yeah, thank you. I see.
Good. Okay. I just remembered that I have something like that for a homework for you, so that's why I'm spending so much time on this. I want to be sure that you can, well, calculate something similar. Okay, one more small problem. Really easy, once again. Strong base. So here we have strong base. Once again, it dissociates. But this case is just a little bit more tricky. So here we have 0.0011 molar solution, whatever. The thing is that when this thing dissociates, for every mole of this substance, we get 2 moles of OH minus and 1 mole of calcium 2 plus. So this basically means that if my initial concentration was this, the concentration of the OH should be double of that, because I create 2 moles of OH minus per each mole of the initial substance. So this is what I get. Well, let me remove this part, it may be confusing you. So the OH minus is basically twice as large as the concentration of this initial substance. Once again, we neglect OH minus from autoionization of water, because that's something like 10 to the minus 7, and this thing is something like 2.2 times 10 to the minus 3. So minus 3 and minus 7, you guess we can neglect that. Okay, and we suppose that there is a lot of water, so on and so forth. We use the equation H plus times OH minus equals to the 10 to the minus 14. So we can calculate the concentration of the H plus. Here we have it. And as a result, we get pH. So that's it. So we calculated the expected concentration of OH minuses. We know that H plus times OH minus should be equal to 10 to the minus 14. And we know that since we added a lot of OH minus, it goes up. The concentration of H plus should go down. And basically we see that when we do the math and we calculate the pH. So pH is now 11.34. And as you remember, anything that is higher than 7 is considered a base. So this is some sort of basic pH, what was actually expected. So we were expecting that because we were adding base to water. So of course we were expecting that pH will be basic. And here is a more complicated problem. You have one such for a homework. This is an example of a weak acid, and that may be a little bit tricky. So yeah. So I want to find pH of 0.1 molar solution of formic acid. So here I have formic acid. It dissociates. I have Ka. In previous cases, we didn't use any Ka. Why? Because we were supposing that acid and base are strong, so they fully dissociate. In this case, we have weak acid. It will not fully dissociate. So some part will be undissociated, some part will be dissociated. Which exactly part is determined by the Ka. So here it is. So in such problems for weak acids, you always should have Ka. If you don't have, you probably should look up in some table. Okay. What do we do now? First, we write the definition of the Ka. Here it is. Concentration of this anion times concentration of H divided by concentration of the undissociated part. Here it is. Once again, we neglect H plus from auto ionization of water. That's pretty reasonable because we have a lot of this acid, 0.1 moles, and despite it's weak, it will still give off a lot of protons. So what now? If we neglect that, we suppose that the number of H plus is equal to the number of these anions that we are left with. So here we have it. And we can write the equation that the number of moles of the undissociated acid, so whatever is not dissociated, plus number of moles of H plus, the same equation you can use with the anion, should be equal to the initial concentration that we had. Does anyone understand this part? So there was 0.1 molar undissociated acid, then part of it transformed into these two species. So this is basically something like number of moles, well, in 1 liter. So this means that whatever, if we add whatever is left, whatever is undissociated, plus whatever has dissociated. But the number of molecules that have dissociated, they transformed in these two species, into H plus and CHOO minus. And basically 1 mole of this gave 1 mole of this and 1 mole of this. So we can add them together to get back the initial number that we had, the 0.1. Okay, if there are no questions, I suppose you understand this part. So now these things get easy. So we have this equation, we have this equation, we have this equation. So we can write down this sort of equation. So I have basically done nothing special. I have transferred this thing to this part. So now I have Ka times the concentration of the undissociated part. And this thing up here, I used this equation to transform that into H plus squared. So here it is. So nothing special happened. Now I say that the undissociated part is basically what we had in the beginning, is 0.1 minus H plus is basically this part of the equation. So this is what I use. And I can, well, this concentration is pretty low, so I can neglect that and say that it's 0.1 Ka, and I do the math, I get this thing. And this is basically that law of Oswald that I have already shown you. So that law of Oswald with that square roots that we had, so let me find it back here. So here it is. So we have just basically derived that for the weak acid, basing on our on our formulae. Good. Okay, for polyprotic acid, these things get a little bit more complicated, so it's always easier to remove the first proton, and it's maybe much more complicated to remove the second and the third and so on. So here are some examples. You can see that if you have, I don't know, some sulfurous or sulfuric acid, you have different Kas. And you can see how do they change, so that they basically drop down when we get from the first proton to the next and so on. So I will not stop at that, just to know that first proton comes off much easier than any of the next. Okay, so one more interesting equation you will probably meet here and there is Henderson-Hasselbalch equation, and probably you will use it somewhere. So here is once again our reaction. Here is the definition of the Ka. I can rewrite it in this way, so I just move H plus to the left and Ka to the right, so nothing interesting. Then I take logarithm, once again nothing special, and minus sign, nothing special, and I use the definition of the pH and pKa. So here's what I get. In most of resources, people like to swap places these two parts, which leads to transforming this minus to plus. And this is what you get. It's called the Henderson-Hasselbalch equation. Very interesting equation, and probably we can use it somewhere. So here you see that pH is equal to pKa plus logarithm of this thing. Once again, I remind you that if we have half dissociated acid, you have A minus equal to HA, so you get logarithm of 1, which is equal to 0, and pH will be equal to pKa. It is sometimes easier to calculate the thing. You can probably suppose, you can probably make some assumptions on these values, so that may be interesting. Okay, titration. Yeah, I guess I still I will show you titration. Okay, and this will be after the break. Yeah. We will use that equation when we will calculate buffers, so that may be quite interesting. Okay, the example of titration. So here is a titration of a weak acid with the strong base. So here we have acetic acid, and I use some strong base, so that basically creates me OH minuses. So base fully dissociates, and I will know the concentration of OH minuses because I know how much base did I add, and I know that it is strong. What happens now? OH minuses start interacting with the acid. Oops. And some part of this acid will be, let's say, neutralized. So protons will be taken away. We will get this sort of anion, and the part of the acid will be left. Now you can ask about pH. So what happens to pH? And this is a perfect place to use the previous Henderson-Hasselbalch equation. So we have pKa for acetic acid, pKa for acetic acid, we know that, and now we have the amount of the unneutralized acid. We can just neglect the fact that that it dissociates, because these concentrations are much larger, and here is the number of here is the dissociated part that was created basically due to the action of the base. So base just took protons, and we know how much of this do we have. And if we divide that, so there is the previous formula, so you see the anion minus divided by the undissociated part. So here we have these numbers, we can divide them, we can calculate this logarithm, and we can calculate the pH. The same situation we can get if we mix weak acid and let's say some salt of this acid, salt with the strong base. This situation is so common that some books even define buffers at the mixture of weak acid with its salt. Salt with a strong, after neutralization with a strong base. Good. So is this point clear, more or less? Okay, I see no questions, so great. So please remember, the last problem at home will be based on something like this. So you will need to calculate how much acid was transformed into this form, how much is left, and use Henderson-Hasselbalch. So buffers. So most cases we use weak acid and a salt, and in most practical cases we suppose the salt is fully dissociated. Here is an example. So why it's called buffer? Because if we add some different acid or some different base to that, it will try to keep pH within some range, some small range. So here we have so-called buffering zone. We have pKa, so it's the best case scenario when you have equal amount of the dissociated and undissociated acid that you have created with that salt. And when you add some acid to that, it will give its protons to the dissociated form, because this is a weak acid, so it will receive that protons. We will get let's say smaller number of moles of this dissociated form, but we will get more of the undissociated form. In the other direction it will work well similarly, but now we are consuming the undissociated form and we are creating the dissociated form. You might be wondering why the thing works and why this is a buffer. So once again I remind you of the Henderson-Hasselbalch equation. So here it is, and what happens if equilibrium is shifted to the left or to the right? The decrease in dissociated form, or increase basically, is compensated by the opposite amount of the undissociated form. So here how that will look like. So this is the function. And here I have just built for you some pretty random function, so it's not even a base 10 logarithm, but a natural logarithm, but that doesn't really matter. What I want you to see is the form of this curve. So you see that before it rapidly goes up and goes down, there is some sort of, that looks like plateau. So basically this is the result of the properties of the logarithms. So that's why we get these sort of plateaus, and that's why buffers are able to basically keep some sort of pH stable. Okay, just a small reminder that we have notable different buffers in the human body. So the first is of course the bicarbonate buffer. It's most important extracellular buffer, especially in blood plasma. So I think we'll get to that at the end of this lecture. I really hope that I will be able to show you everything I have. After we get out of these formulae, we will get to something pretty biological and I guess pretty interesting. Phosphate buffer in the intracellular fluid, some protein systems that buffers via ionizable side chains, often histidine imidazole group, and hemoglobin buffer. So that's what we have. Okay. I guess I show you this one more slide and we can make a small break. Good. Here is the case of mixing two acids. So what if we have two acids added to the to water? So we have two reactions. So here is the first one. So acid 1 may give its proton to water. Acid 2 may do the same. I suppose that for both acids we have these sort of coefficients. So they are just defining basically strengths of the acid. And we know that there should be some sort of mass balance. So if I have added certain amount of the acid, HA, at the beginning of the reaction, after all these things are settled, we have part of dissociated and part that is undissociated. And their sum should be basically equal to what I have added at the beginning. Well, that's pretty reasonable because it doesn't go anywhere from the container, so it's just retained in there. The same is true for the acid number 2. So here we have it. Okay, and we have so-called charge balance. So we create the number of positive charges the same as we have negative anions. Pretty okay. If we collect everything together, we will get some sort of these formula. Well, I don't expect you to get deep into these formulae. What I want you to notice, we can write a third order equation on H3O plus from this. If we can include auto dissociation of water, but then it will be fourth degree equation. But anyway, we can calculate pH in this case, in the case of mixture of acids. That will be something pretty complicated, and there will be a process of protonation of one acid by another acid. So here it is. So here I have written an equation that describes this sort of process. If I take K1 and I divide it by K2, I just use these sort of definitions, I get this K, but you see that some parts I can divide through. So I do division. So this thing goes away and this goes away. Now this will go up and this will go down. And here is what I get. And this sort of equation corresponds to this process. So when mixing two acids, you get something like one acid is protonating another acid. So that's what we get. Okay. Do you wish some sort of small break? Okay, strange silence.
We were putting reactions. Thumbs up.
Okay. Okay, then let's make a small break, I guess, for 10 minutes.